Welcome to virtual algebra class. So let us talk about the perfect squares. First of all, yes, you guys might know that when I say square, I'm referring to the power of 2, the exponent 2. For example, if a mathematician looked at this problem, a lot of GED students will say, that's 7-2. That is not 7-2. That is 7 squared. 7 squared. Squaring is an actual real-life thing you do in math class. Just like you can add, subtract, multiply, or divide with numbers, you can also square them, raise them to the second power. Okay, now I have a lot of students who tell me, Kate, 7 squared is 14. And they're wrong, but I can tell, I understand why they do that. Our brain kind of automatically wants to multiply these two numbers together, revert back to something we're used to. And so I get the answer 14 a lot, but it makes me giggle. I know something about the number 14, and that is no matter how much I arranged 14 things, I could never make a square. Let me show you what I mean. Like imagine 14 things. You could make, 2 rows of 7. You could make 7 rows of 2, or maybe I flipped that around. Maybe I did 7 rows of 2 the first time, and now I'm doing 2 rows of 7. But still, those would both be rectangular shapes. They're not squares. I could do 1 big long row of 14. Again, rectangular, not a square. So what does it mean for something to be a perfect square? It means I could actually take that number and arrange it into a square. Great example is the number 9. So I'll show you what I mean here. So I couldn't do that with 14. 14 wouldn't make a square. 14 wouldn't make a square. 9 would. Let me show you what I mean. I could take 9 things and arrange them in a 3 by 3 perfect square, a shape that has just as many rows as it does columns. Does that make sense? That's why these numbers are called perfect squares, because they could literally form a square. Okay, so let's go ahead and look at the actual list of perfect squares. So let's talk about the perfect squares. Again, the perfect squares are a list of numbers raised to the second power, and I'm going to start with 0 squared. 0 squared is a little interesting because it's hard to think about a square with 0 dots. It doesn't make any sense. But still, what I'm saying here is to take 0 and multiply it by itself, just like the area of a square formula is s squared. It is just like that. So 0 times 0 would, of course, be 0. That one's pretty easy and a little silly to think about. So is 1 squared. Because if you think about if you had one item or 1 unit, maybe we'll think about 1 square unit since we've been doing area, it would be 1 high by 1 wide. So 1 squared is just 1. Again, not very exciting, but as soon as you get to 2, I hope you'll be able to see what I mean. 2 squared means stacking something 2 wide and 2 high. And you can see if I did that, if I had a 2 by 2 square, it would be composed of how many total little squares inside of it? 4. 4. 2 times 2, or 4. Again, just like the area of a square formula, you're just multiplying the 2 dimensions. So when I say 2 squared, I'm saying multiply 2 by itself. Same thing for 3 squared. I'm not saying 3 times 2, I'm saying 3 times 3, or 3 times itself, which of course would be that square of 9 we were looking at before. Now, this is a list of numbers that you should have memorized. And I gotta tell you that I do not take asking you to memorize something lightly. You're talking to the woman who, before she was a GED teacher, was a tutor to adults with disabilities. And I worked with adults who could not memorize their times tables. Like they literally could not. They would memorize their 7s and their 6s would be gone. They would memorize their 8s and their 7s would be gone. Due to some various learning disabilities or traumatic brain injuries, they just did not have the memory to memorize their times tables. That being said, I taught them to do all the math without memorizing their times tables. But the perfect squares, if you were to only memorize 2 things in math, I would ask you to memorize the perfect squares and the 7 times tables. Just that. That would be it. The 2 most important things I can think of to have your math facts memorized on. Everything else, I'll just go the long, slow way. Okay? These are that important to memorize, and I'll be explaining why as we move on. But we're going to keep going compiling this list here. So 6 squared would be 6 times 6, which would be what, ladies?
36.
36. And 7 squared, the one we were talking about, would be not 14, but
49.
49. Beautiful. And I'm actually going to go up higher than we usually go. We usually only have memorized up to our 10 times tables, But I always suggest to students that they actually know their perfect squares up to 15. And again, the reason why is because I promise it'll make your life a lot easier. So most of us know 10 times 10 is
100.
Mm-hmm. And a few of us even know 11 times 11. Do you know that one?
I think it's 122.
Yeah, if you're not sure, let's let's compute it. So to compute it, I would just take the number 11 and multiply by 11. Let's check it out. 1 times 1 is 1. And of course, 1 times 1 is 1 again. Now, when I go to memorize, you see it now?
Yeah, a little bit. I got a little bit mixed there.
Yeah, most people do. When I go to memorize, multiply 1 times 1, I get another 1 and then another 1. And I add that up and I get 121. And serenity, I just want to point out that the reason why I knew that was wrong was because I knew it had to be odd. Can I say that again? I knew it had to be odd. Look at this list. Notice that every time I square an odd number, like 1 or 3 or 5, what kind of an answer do I get?
Odd.
Exactly. Odd number, odd answer. This will actually come up in handy later. When I squared an odd number, I got an odd answer. Let's look at when I square an even. When I squared an even, I got an
even number.
Even. Yes, exactly. So anyway, next one I'm going to do here, I'm going to square 12 and 12 times 12. Anybody know that one?
144.
It is 144. Nice. And the next one I'm going to do, I would assume most people do not know. 13 squared is 13 times 13. So I can do it in some side work here. My paper's getting all messy. So 13 times 13 gives me 9. Again, if you don't know it, you can do it like this, but it'll help you later to know it, I promise. You'll see some problems where you'll want to have them memorized. And I get 169. Okay, and then 14 times 14, I always remember because it's just like the last one, 196 or 169, but the orders of the 6 and the 9 get flipped around. It's 196. And then last one I'll ask you to have memorized today, and I really wish I had enough room for it in my list. I'm going to squeeze it in, is 15 squared, or 15 times 15. So 5 times 5 is 25. And then 5, 6, 7, 5, and 1. I end up with 225. So squeeze that in if you can. 15 squared is equal to 225. This is the list of numbers that would really, really behoove you to memorize. So when I go to give you the practice today, I do have a Quizlet set called Perfect Squares for Beginners. I'll put that up in our practice so you'll see it. For those of you just watching on YouTube, I'll drop it in the comments. Okay, so I have Quizlet Perfect Squares for Beginners. You'll want to play with that one as much as you can to memorize it. And if you played in what's called space race mode, that's a really good way. I think it's called space race. Okay, so that's the one I want you to have memorized. Let's talk about all the reasons to have this list memorized. As it turns out, this list of perfect squares has a ton of different applications on the GED. First application, and one of the most important we need to know for the Pythagorean theorem, is the opposite, the inverse of squaring. Well, we've been talking about this a lot, actually. We've said before in this class that all these operations have an inverse, right? We talked about like the inverse operation of addition is subtraction. The inverse operation of multiplication is division. And now we're talking about a new operation, squaring, and it also has an inverse. Do you guys remember what the inverse of square is?
Square root.
Exactly, square root. So what square root will do will take us back from these answers, this list of perfect squares, and take us back to the side length of that square, or where that number came from. So I'm going to have you make another list right next door, square roots. Let's compare the two. Remember that square roots have that little check mark house over them known as the radical. Yes, that's called a radical. Isn't that radical? Yeah, math humor. Anyway, I'm the only one who laughs at my math humor. It's fine.
It's dry humor probably to people.
So here we go. We're going to start with what was the answer. So like in this case, 0 was the answer. When I take the square root of that, I'm going to get back to where I came from. Now, of course, just like before with 0 and 1, it'll be a little boring because it was the same number. But starting with the next perfect square. So what I'm going to do is I'm going to take the square root of the perfect square. My next perfect square after 1 was 4. 4 was the next number that I could make a perfect square out of. So I'm going to take the square root of 4. Now I'm asking myself, when I take the square root of 4, I'm asking myself, what number times itself equals 4?
2.
Exactly. If we have that list memorized on the left-hand side, we will not struggle to see that we are going back to the number 2 because 2 times 2 is equal to 4. Now notice I don't have a little square on there. I took the square root of 4 and it brought me back to 2. Let me finish writing this down. Okay, so let's take the square root of the next number after 4. The next perfect square after 4 was 9. We could arrange a 3 by 3. So the perfect square, or the square root of 9 would be 3. I'm getting back to the root of what 9 is made of. 9 is made of 3 times 3. Okay, so help me compile the rest of the list. What would be the next perfect square that I could take the square root of?
16.
Exactly. So the square root of 16 would be 4. And I'm just going down this list that I had on the right before. The square root of 25 would be 5. The square root of 36 would be 6. And we'll compile this list. If you're watching, I highly suggest you pause me. Make me shut up right now. See if you can compile this list. If you can make it using the list on the left, you will be more likely to remember it. And I'm going to run out of room again. The square root of 144 is 12. The square root of 169 is 13. Apparently, with the size of my handwriting, you guys really only have to go up to 14. The square root of 196 is 14. And the last one I would have written, if my handwriting wasn't so large, is the square root of 225 is equal to 15. Get that all in a column so you can see it if your writing is better than mine. Okay, so basically, if you know these perfect squares forward, you will know the inverse. And this is really, really good news because there's something I have to warn you about square roots. Square roots are the first operation without an algorithm. Now, a lot of my students look at me real blank right now when we have this conversation. What do you mean they're the first operation without an algorithm? They don't even know what the word algorithm means. Well, it turns out you've been using algorithms since about 2nd grade, maybe even before that. There's a lot of math facts you have memorized. Like if I say to you, what's 1 plus 5? Nobody needs to think about that. Most people are just like 6. You guys don't do any scratch work usually for 1 plus 5. You don't. But then I'll give you another problem. I'll be like, what's 17 plus 35? And then students, we don't usually have 17 plus 35 memorized. So then that's when you come over to your scratch paper and you start lining up 17 and 35 and you do all the adding and the carrying and all the stuff that you guys have known how to do since an early age. Those are the algorithms. That's what I mean, okay? So notice what I just said. Square, and I forgot a word in my notes. Add it in if you're copying me. Square roots are the first operation we've seen, at least in our classes, without an algorithm. What does that mean? That means I don't have a step-by-step process to just simplify it if you think about that. The only thing I have is my common sense. And by memorizing those perfect squares, that's what's going to do to be able to get your answer. So shall we look at some applications of this? You could have an order of operations problem or an algebra problem that just includes a perfect square in it that you just have to do. So for example, 11 squared could just pop up. So that being said, we already constructed this list. This should be very simple for us. Hopefully we have this one memorized. But remember, 11 squared does not mean 22. It means you have a square that's 11 by 11. And its total area would be that perfect square of 121. 21. Beautiful. So it could be something that simple. That'd be nice. Again, if you saw that it'd be inside of an order of operations problem or inside of an algebra problem, you probably wouldn't just see that by itself. Okay. That being said, you might also see just a straight, I actually wanted to do this one because students mix this up. I wanted to do the square root of 9. Okay. So square root of 9. Now I'm talking about a square that has 9 little individual squares over it. I'm trying to get back to the root. I'm trying to get back to just the side length. What size square is composed of 9 individual squares? It would be a 3 by 3. Does that make sense? So I'm asking myself what number times itself equals 9? Of course, 3 times itself equals 9. Careful, I'm not halving it. For some reason, if I do an even number like 16, a lot of students instantly flip into halving it and they write 8 there. But the square root of 16 isn't half of 16. The square root of 16 is what number times itself equals 16. And of course, 8 times 8 would be way too big. So you guys help me out. What number times itself would equal 16?
4.
4. Beautiful. So it's super simple. It could also show up, you know, in words, buried in a word problem, various things like that. So watch out for just these kinds of expressions written out in words. So if I said to you, what is 14 squared? Well, of course, we know 14. Squared means that little floating 2. And what is, we're asking ourselves, what is that equal to? So, of course, it's not 28, right? 14 squared means 14 times 14. And if you had forgotten it, you could always multiply it out. And you would indeed see that I was right. It is 196. So let's try, what is the square root of 25? Of course, if they just said, what is the square root of 25? They're taking us to take the root. So we do make that radical sign of 25. What is that? Okay, we'll simplify. So obviously the square root of 25 is 5. So let's look at the implications of this. Go back and look at your notes for those square roots we wrote down. That was the right-hand side, right? All the roots with the radical houses. Like notice we wrote that the square root of 9 is equal to 3 and the square root of 16 is equal to 4. But we said absolutely nothing about the square root of 13. We didn't take the square roots of anything that wasn't perfect. We only took the square roots of the perfect squares, didn't we? So how in the world are you supposed to figure out something like the square root of 13? Well, notice the square root of 13 falls between the square root of 9 and the square root of 16, doesn't it? Mm-hmm. We know the answer to those two problems. Even if we don't know the square root of 13, we know that the one before it, the square root of 9, is 3. And the perfect square after it, which is 16, so its square root, the square root of 16, is 4. So we should realize at least that even though we don't exactly know what the square root of 13 is, we know it lies somewhere between 3 and 4. Just like the square root can be sandwiched between two perfect squares, then the answer could be sandwiched between the two answers there. And if you were to do this in your TI, you would want to make sure, first of all, I'm trying to get a decimal out of my TI. Remember what mode I have to be in to get a decimal out of my TI? It's classic mode. So I hit mode, and now I'm on this screen here, and on the last line it says classic. So I arrow over the word classic and I press enter. I make sure I'm in classic mode. Then I clear out of my screen to get out of there. And now I'm going to take the square root of 13, and I will see indeed that I get something around between 3 and 4. I get 3.6, yada, 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 yada. Does that make sense? But even without a calculator, you can estimate these things if you know the perfect square. You know, it's like 3 and something. And that is a very, very useful skill, as it turns out, that we'll need. Okay, so let's try estimating some more. So let's get out some examples here. Say the square root of 40. If you saw something like this on the GED, I would expect it to be on the non-calculator section. But this skill is also useful in multiple choice questions, okay? So the square root of 40 is between which two consecutive integers? So don't get frightened by my language. Consecutive means just like in a row, one after the other. And integers are those numbers that you're used to, 0, 1, 2, 3, 4, 5, all those wonderful whole numbers. And their opposites, the negatives. Which two consecutive integers? Let's see. I'm going to give you some selections here. Again, if this were on the GED, you'd probably have selections. Again, if I was doing something like this, 40 is not a perfect square. And so I don't know its square root. Without a calculator, I'm a little lost, but I can at least estimate it. I can get a decent answer by putting it between two perfect squares I do know. So I'm constantly running through that list of perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9. 1, 4, 9, those are the perfect squares I'm talking about. So there's a perfect square that comes right before this. That'd be 36. So I know I can peg the square root of 40 between the square root of 36. And the perfect square right after that would be 49, the 7 times 7 one. So I see that I can peg the square root of 40 between the square root of 36 and the square root of 49. Now, even though I don't know the square root of 40, I do know the square root of every perfect square. So the square root of 36 is, of course, 6. And the square root of 49 is, of course, 7. So the answer to this would have to be somewhere between 6 and 7. Now, I don't know exactly what without a calculator. Even before the age of calculators, engineers used to carry tables of square roots because, like I said, this is the first operation without an algorithm. Really, all I can do here is make a guess and check. Now, you can make good guesses using a lot of common sense, but still, guess and check is my only problem-solving method I have here. No algorithm. The square root of 100 and 9 is between which two consecutive integers? And again, anytime I do square or square root problems, I'm running through that list of perfect squares in my head, which is one of those reasons I just beg you to take the time on Quizlet to have them memorized. Because if I'm taking the square root of 109, I don't have an algorithm. I don't want to guess and check and guess and check and guess and check to the end of time. I want to use some common sense here. What two consecutive integers am I between? Let's sandwich it between two perfect squares that we do know the square root of. So like 6 times 6 is 36. I'm nowhere near high enough. 8 times 8 is 64. I'm getting closer. 9 times 9 is 81. Looking pretty good. 10 times 10 is 100. Now I'm getting real close. 10 times 10 is 100. So I'm somewhere between the square root of 100. Okay. And then 11 times 11, as we know, would be 121, which is bigger than 109. So I'm somewhere between the square root of 100 and the square root of 121. Make sense to you, ladies?
Yes.
Well, then my answer, my actual square root, would be somewhere between the answer to this. What is the square root of 100?
10.
10.
And this, the square root of 121 is?
11.
11. So this guy must be between 10 and 11. I need to find out if you guys possess a skill that we teach early in math, but a lot of students don't catch on to. So it's going to seem like I'm sidetracking, but I promise you, I'm going to bring us into the loop. This will apply to perfect squares in just a second. But I'm wondering if you know how nice it is to multiply with round numbers. And when I say round numbers, I mean numbers that end in 0. That's all I mean. Nice, easy numbers to multiply with. For example, if I wanted to multiply 200 times 7,000, I would not do any scratch work. Whoops. I would not do any scratch work. You guys are all doing scratch work sometimes on the side of your paper. There's zeros everywhere. You're getting all in a muddle and you're lost, and I'm home drinking tea already because I did this problem in my head. When you see numbers that end in 0, you are actually able to just multiply the non-zero portions of this. So I can multiply 2 times 7. 2 times 7, of course, would give me 14, and then I can consider all the zeros. And when you multiply, place value accumulates. I'm going to say that again, because this is always true, even like with multiplying and dividing with decimals and things like that. Place value accumulates. So all these zeros here are going to add up. I'm going to end up with 1, 2, 3, 4, 5 zeros. And if you're having trouble saying that number, you could just come from the back 1, 2, 3, comma, 1, 2, 3, comma. I didn't need to do any math or any side work to do that. I was able to do that all in my head because that beautiful principle of those place values accumulating, those zeros, just stacking up the back of my number. So should we try one more before we apply this skill to square roots? Let's be nice and gross. Huge numbers. Okay, again, I do not need side work. I do not need zeros all down the side of my paper because I can see all these trailing zeros do not have to get involved in my multiplication until the end. I can multiply just the non-zero portion, 21 times 3. And I'm able to do that in my head because there's no carrying involved. You know, 3 20s is 60 and 3 1s is 3. I get 63. And then my place value is going to accumulate. So I'm going to get all these zeros. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And even if you can't read that number, you can do that math, okay? I can read this number though. 1, 2, 3, comma, 1, 2, 3, comma, 1, 2. 6,300,000,000,000.
That'd be nice.
Yeah, I would think in money. It'd be nice if it was positive, but if it was negative, you'd be in a world of hurt, girl. That sounds like that's not even as bad as our national debt right now.
Right?
I think it's in the trillions, I'm fairly certain. So easy, right? Zeros tack on. Well, we can apply this skill to our perfect squares. Take a look. And I want to talk about what I call round perfect squares. I'm telling you, there was a reason why I asked you to memorize that list, why I want you to memorize that list. If you have that list memorized, you'll also have this list memorized by default. I'm going to start with I'm basically looking at the 10 times tables, okay? If I square 10, we already know that one. 10 times 10 is 100. But I want to point out something to you. Why is 10 times 10 100? It's 100 because 1 times 1 is just 1, and then I end up with those 2 zeros of place value. 2 zeros of place value. So if I can square 10, I can square any number on the 10 times tables, like 20, for example. Again, if I were to do that, 20 squared would mean 2 times 2. Well, we already know what 2 times 2 is. That's that list of perfect squares we had memorized. 2 squared, or 2 times 2, is 4. And then I'd end up with how many zeros? 2 of them again.
2.
Exactly. And that pattern's going to continue. Take a look. 30 squared would be 3 times 3, or 9, that perfect square of 3, with a couple of zeros on its backside. 40 squared would be that perfect square of 4. So not 4 times 2, not 8. That perfect square of 4. 4 times 4, which is 16,
16.
with a couple of zeros on its backside. 50 squared, we'd get that perfect square of 5, again, with oh, I thought one of you guys were saying, oh my God.
Sorry.
No, it's okay. I just think it's funny. I was all excited like you were having mind-blowing moments, but so 80 squared would be my 8 squared, 64 with a couple of zeros on its backside. What would 90 squared be then, ladies?
8100.
Exactly. And again, it's just that list of perfect squares now with zeros on it. Even 100 squared isn't that bad because I can square the 1. And then let's think about how many zeros we'd end up with. We'd get those 2 zeros 2 times for a total of 1, 2, 3, 4 zeros. And you see those zeros kind of doubling.
Yes.
And I can almost give myself a little shortcut. I could just square the non-zero portion and double the zeros. I just want to think, is it your daughter or your son, Saleha? Are you
Daughter.
Daughter? I just want to think she's amazed and she's just astounded by math. She's going to grow up to be an engineer and she's going to support her mother in her old age.
Okay.
Exciting, super exciting. So nice shortcut. If you don't remember it, don't worry about it because you can always come up with it. But again, just knowing those perfect squares made us know a whole nother list of numbers, large numbers, which you wouldn't necessarily expect. And we're going to use this list again. But once again, I say, if you know the round perfect squares, guess what? You also know the round square roots. And every time I call anything that's square rounds, my class laughs at me. They're like, how's it a round square? Again, when I say round, all I meant is that it ends with a 0. And of course, the square and square roots refers to that second power. Okay, so again, if you can work it forwards, you can work it backwards. So that means that I can take the square root of 100, which we already knew was 10. But I could also take the square root of 400. I can square root the non-zero portion. So the square root of 4 is 2. And then I can just end up with half the zeros this time because 20 times 20 would be 400. And so on and so forth. The perfect square that I had before here, 900, could be square rooted to get back to 30. And of course, 1600 could go back to 40, and so on and so forth. And let's complete this list here together. Square root of 3600, of course, then would be 60. And I really want you guys to see this pattern. I'm square rooting the 49, 7, and I'm taking half the zeros because of that principle of place value. Adding up when you multiply, we're going to see us getting half as much when we take the square root. It'll double when we square, half as much when we square root. And so if I were taking the square root of 10,000 here, the square root of 1 is 1, and then I'll get half these zeros, I would just get 2. So again, you could square root the non-zero portion and take half the zeros. Now, of course, this only works for round numbers, but what a nice trick. I also have practices for both these things in Quizlet, just straight up doing these skills. We'll look at some application problems of that, and then we'll be done. It'll be a miracle short class. Okay, let's do some examples. Let's start really simply. 70 squared. Again, you could go to the side of your paper and you could multiply 70 by 70, but you don't have to if you understand the perfect squares. So we'll start with the perfect square of 7, which is what? 7 times 7 is?
49.
49.
And then we will get double those zeros because we actually have 2 70s multiplying. We'll end up with the 2 zeros from the back of the 2 70s. And so, of course, I get 4,900. So if I wanted to work backwards, I wanted to take the square root of 1,600. Again, I could take the square root of just the non-zero portion here. So the square root of 16 is
4.
4. And then I would get half the zeros. So instead of 2 zeros, I would have just 1. And why is that true? That's true because 40 times 40 is equal to 16 and 2 0. So let's look at an implication of this. Again, we get the power of estimation. Could be multiple choice where we're just approximating, we're just finding a range. I find this less likely on the new GED. You probably wouldn't have something like this, but this skill comes up in other contexts. So let's make sure we can utilize this skill. But the square root of 784 is between what two numbers? Well, let's think about it. 10 times 10 is 100, so that would be the square root of 100. See how I'm working backwards? I always work backwards. Instead of square rooting, I deal with perfect squares. And then 20 times 20, of course, is square root of 400 is 20. So, I'm too small here. Come down here. Of course, 20 times 20 is still 400. 30 times 30 is 900. And see how the square root of 784, I might not know, but I know at least it's somewhere between 20 and 30, since it's the square root of 784 would be somewhere between the square root of 400 and the square root of 900. Very similar to those estimating problems we did earlier. Then we can use the skill even more, and we can refine our answers when we have a multiple choice answer. Let me show you what I mean. Okay, so I have 4 possible answers here. What is the square root of 1936? Now, that's a great big number. Without a calculator, I'd be in a lot of trouble, but I can at least estimate it between 2 round numbers. Even though I might not know the exact answer, I can start by estimating between 2 round numbers. Again, I don't have an algorithm for finding the square root. You can't just do something simple like divide by 2. All you have is your common sense. And so our first step of common sense would just be to estimate it. I'm thinking to myself like, okay, 20 times 20, 10 times 10 is 100. 20 times 20 is 400. I'm thinking of those round perfect squares. 30 times 30 is 900. 40 times 40 is 1600. And 50 times 50 is 2500. And now I've kind of pegged myself. I know that 1900 must be somewhere between 1600 and 2500. Does that make sense to you guys?
Yeah.
So therefore, the answer must be somewhere between 40 and 50. And that's really nice for a multiple choice problem, because in this one that I wrote, I only have one number between 40 and 50, don't I? 44. Now, of course, whenever you guess on anything, you should guess and check. Wise mathematicians don't just guess. Sometimes we guess, but when we do guess, we check. So we should go back and check that. How can I check that number? By squaring it. The opposite of square root is square. So just take that number, square it. See if you get right back to 1936. So 44 times 44, well, 4 times 4 is 16. That's another 16, 17, 16 and 17 again. And I get 6, 13, carry a 1, 1936. I do indeed get 1936. And so not only did I make a decent guess, I checked my decent guess. I have carried the common sense with square roots so far in my classes before that I've shown them how to find the square root of large perfect squares like this, like the square root of 1936, no calculator, no multiple choice. So you can use your common sense and your estimating skills and a lot of other things to help you make really good guesses that you check, but it takes a long time, it takes a lot of logic. You'll really want your calculator to do this. So let's review one more time how to take the square root on a calculator to check our answer here. So if I were to wanted to check this square root of 1936 in my calculator, again, to do square root, make sure first that you're in classic mode. If you're expecting a decimal answer, now there's a time and a place to be in math print mode and to get a different kind of answer, but we haven't talked about it yet. Okay, most of the time you usually want a decimal answer to these kind of problems. So, and then you take second. Because the square root thing is in green, you'll need to press the second button first, and it's right above the x squared button. Careful, people press the other one and get wrong answers. So second, square root, and then you can type in your 44 and press enter. Oh, not my 44. What was I supposed to put in there, ladies? 1936, sorry. And press enter, and I get 44. So indeed, I was correct. Check. Well, thank you for joining me. Super glad not to be talking to myself once again, and I'll see you next week. Math is always easy when the math teacher does it. Now it's your turn. Don't move on without giving this skill a try.